Welcome back to G Fun Facts Online. Today we are going to dismantle a timeline that cosmologists have held dear for decades. If you open a standard textbook on the history of the universe, you will find a story of a slow, methodical builder. The narrative, known as the Lambda-CDM model, tells us that the cosmos began in uniformity. It suggests that after the Big Bang, the universe was a place of subtle gradients, where gravity worked gently over billions of years to sculpt the first large-scale structures. According to this standard script, the early universe was a nursery of cold, dark matter halos, slowly coalescing, with the fiery, chaotic energy of massive galaxy clusters only emerging much later, towards the Middle Ages of cosmic history. But in the frozen reaches of the southern sky, a single object has shattered this timeline. It is known as SPT2349-56. To the uninitiated, it looks like a smudge of radio waves from the dawn of time. But to the astrophysical community, it has become known as the SPT2349 Anomaly, a paradox of early cosmic heating that simply should not exist. We are looking back at a time when the universe was only 1.4 billion years old, a mere tenth of its current age. We expected to find a cold, formative nursery. Instead, we found a fully ablaze inferno, a cauldron of over 30 galaxies packed into a space the size of the Milky Way, swimming in a bath of gas heated to millions of degrees. It is too big, too fast, and above all, too hot. This is the story of that discovery, the crisis it has triggered in our understanding of the universe's timeline, and the terrifyingly violent nature of the cosmos' first billion years. The discovery of this object began not with a bang, but with a shadow. In the high-altitude deserts of Antarctica, the South Pole Telescope, or SPT, scans the sky for the cosmic microwave background. This is the afterglow of the Big Bang, a steady hum of microwave radiation at 2.7 Kelvin. This light is ancient and remarkably uniform. However, when this light passes through a massive cluster of galaxies, it gets distorted. The hot electrons in the cluster's gas kick the photons to higher energies, creating a distinctive dip in brightness. This is called the Sunyaev-Zeldovich effect. In 2010, the telescope detected a faint signal in the constellation of Pictor. It was catalogued as a curiosity, just a distant blip. But years later, when the Atacama Large Millimeter Submillimeter Array, or ALMA, in Chile, turned its 66 high-precision antennas toward the object, the true magnitude of the anomaly was revealed. Usually, at a redshift of 4.3, which corresponds to looking back 12.4 billion years, astronomers expect to see protoclusters as loose associations of galaxies. They should be drifting toward each other across tens of millions of light-years, appearing as diffuse, ghostly webs of gas. SPT2349-56 was different. It wasn't a loose web, it was a train wreck. ALMA revealed a tight knot of over 30 massive, star-bursting galaxies crammed into a volume of space less than 500,000 light-years across. To put that in perspective, imagine taking the 30 largest galaxies in our local universe and squeezing them all into the space between the Milky Way and our satellite dwarf galaxies. It is a traffic jam of galactic proportions. But the real shock came recently, in January 2026. When a team led by researchers from the University of British Columbia and Dalhousie University published a new analysis on the temperature of the gas between these galaxies. Lead researcher Daji Cho noted that they expected the gas to be cold. At this age, gravity should have had time to shock heat the gas. It should be forming stars, yes, but the space between galaxies should be relatively temperate. Instead, the thermal signature was blinding. The intracluster medium of SPT2349-56 was glowing at temperatures exceeding 10 million degrees Kelvin. It was 5 times hotter than theoretical limits allowed for a structure of that age. It was hotter than many massive galaxy clusters seen today, which have had 13 billion years to heat up. The universe had effectively built a blast furnace in the middle of the Stone Age. To understand why this heat is so disturbing to theorists, we have to look at how cosmic structures usually get hot. In the standard model, heat is a byproduct of time and gravity. As a galaxy cluster forms, dark matter pulls gas inward. As this gas falls into the deep gravitational well, it accelerates. When it hits the center, it crashes into gas falling from the other side, creating virial shocks. This converts the energy of the fall into heat. But this process is slow. It takes billions of years for a cluster to become massive enough to generate this kind of heat naturally. SPT2349-56 cheats this logic. First, there is the mass problem. At one point, 4 billion years post-Big Bang, the universe wasn't dense enough in any one spot to easily accumulate the quadrillion solar masses needed to generate this heat. Second, there is the time problem. Even if the mass were there, the settling of the cluster takes time. This object appears to be pre-virialized. It is acting like an old, evolved cluster while it is still in the womb. As astrophysicist Dr. Scott Chapman remarked, "It is like walking into a nursery and finding a newborn baby who is 6 feet tall, has a full beard, and is smoking a cigar. The timeline simply doesn't fit the biology we know." If gravity didn't heat the gas, what did? This question has led to the proposal of a mechanism that changes our view of the early universe called catastrophic feedback. The sheer density of SPT2349-56 offers a clue. The galaxies inside are not passive. They are starburst galaxies on overdrive, churning out stars at a rate of 10,000 solar masses per year. For comparison, the Milky Way produces about 1 star per year. This furious rate of star formation results in massive stellar winds and supernovae explosions. Furthermore, buried within this chaotic scrum are at least 3 supermassive black holes, active galactic nuclei, that are devouring matter and spitting out relativistic jets of plasma. The paradox of early heating suggests that in the early universe, these feedback loops were not gentle regulators, they were violent, explosive drivers. The black holes in SPT2349-56 aren't just heating their host galaxies, they are blasting energy out into the intergalactic void, preheating the entire cluster before it even finishes forming. This implies the early universe was far more violent than our simulations predicted. It wasn't a slow gravitational buildup, it was a detonation. But the anomalies extend beyond temperature. They challenge the speed limit of cosmic structure formation. In 2025, ALMA observations revealed another piece of the puzzle, a massive, diffuse reservoir of molecular gas extending across the entire protocluster. This hidden fuel tank was invisible to earlier scans. This reservoir contains enough raw hydrogen to power the cluster's star formation for another 400 million years. Its existence explains how the cluster can be forming stars so fast, but it deepens the mystery of how it got there. In the hierarchical model of structure formation, small halos form first, then merge to form bigger ones. A structure as massive as SPT2349-56 should be the end product of billions of years of mergers. To have such a massive concentration of gas and dark matter in place by redshift 4.3 requires the initial density fluctuations in the Big Bang to have been improbably high in this specific region. It is a statistical outlier of the highest order, a sigma event so rare that finding one in the small patch of sky surveyed by the South Pole Telescope suggests they might be far more common than theory allows. If objects like this are common, it means the early universe was clumpier than we thought. It suggests that the seeds of structure laid down by cosmic inflation were not as uniform as the standard Gaussian distribution predicts. This anomaly pulls at the loose threads of the Big Bang theory itself. SPT2349-56 is also the poster child for a cosmological problem known as downsizing. In the 1980s and 90s, theorists believed that small galaxies formed first and big elliptical galaxies formed last, but observations have consistently shown the opposite. The most massive galaxies with the oldest stars seem to have formed very early, then shut down. SPT2349-56 is the smoking gun for how this happens. We are witnessing the brutal rapid assembly of a massive cluster core. The galaxies inside will eventually merge to form a single, gigantic elliptical galaxy, a brightest cluster galaxy that will anchor the cluster. Standard simulations predict this merger process should take billions of years. In SPT2349-56, the galaxies are so packed that they will likely coalesce within a few hundred million years. This system is effectively fast-tracking evolution. It is building a massive, red and dead elliptical galaxy when the universe is barely out of its infancy. This forces a rewrite of galaxy formation models. It means that the mechanism for building the largest structures in the universe is not a slow accumulation, but a rapid, explosive collapse, followed by a sudden quenching of star formation due to the extreme heat of the surrounding gas. The 10 million Kelvin gas observed by ALMA is the quenching agent. It is so hot that it cannot cool down enough to fall into galaxies and form new stars. The black holes have heated the cluster so effectively that they have cut off the food supply for future generations of stars. This cluster is essentially committing suicide by overheating, ensuring that the massive galaxy it leaves behind will remain dormant for the rest of time. The existence of the SPT2349 anomaly places uncomfortable pressure on our understanding of dark matter. Dark matter is the invisible scaffolding of the universe. We cannot see it, but we simulate it. Our best simulations, like the Millennium Run or Illustris, struggle to produce a dark matter halo massive enough to host this object so early in the simulation's clock. To make a halo this big, this fast, we might need to tweak the properties of dark matter. Is dark matter colder than we thought, allowing for sharper clumps? Is there a non-Gaussianity in the primordial density field, a result of complex physics during inflation? Or is this evidence of self-interacting dark matter, where dark matter particles can collide and clump faster than standard theory predicts? The anomaly has sparked a race among theoretical physicists to see if they can break their models to reproduce SPT2349-56 without breaking the rest of the universe. So far, the results are inconclusive. The cluster sits right on the edge of what is mathematically possible. We used to think of the deep past as a dark age, a quiet time before the lights turned on. SPT2349-56 teaches us that the dark ages were actually an era of cosmic fireworks. This single object, a speck in the southern sky, has revealed that the young universe was a place of extreme density, hyperactive black holes, and gas heated to impossible temperatures. It challenges our timelines, our gravity models, and our understanding of how galaxies die. As we turn the next generation of telescopes, like the James Webb Space Telescope and the Future Square Kilometer Array, toward these distant epochs, we are likely to find that SPT2349-56 is not alone. It is likely just the tip of the iceberg, the first beacon revealing a hidden population of monsters in the early dark. The universe, it seems, did not wake up slowly. It woke up screaming,